Hi, in this video, we want to take a look at partitioning data in R. Okay, so the situation that we are in is that we want to build a predictive model. All right, so our true goal is to build basically a crystal ball off of data. I want to predict the future and I want to make the best possible predictions possible. Okay, so what I'm going to do, I am going to go through the process of preparing my data. I'm going to get my data, I'm going to prepare it, get it all nice and pretty, get it ready to go. I'm going to build a bunch of models. I'm going to build several models. Then I'm going to look at these models. I'm going to only use one or maybe a few, probably just one model. And then I'm going to make a prediction with that one model. And then I'm going to hope that I made good predictions. All right. I mean, does this sound like a reasonable thing to do? Like if I'm trying to make predictions, I don't know if I'm making a good prediction until it's too late. That's something to be mindful of. And ultimately, if we knew what we were doing, we wouldn't be using data. So that's always something to be mindful of, is that whenever somebody's using data and statistics and machine learning, artificial intelligence, stuff like that, they don't know what's going on. If they knew what was going on, they wouldn't be using data. All right, so what we want to do, we want a framework to be able to know, hey, I'm going down the right track on making a prediction or not. And sometimes you might be in the position that you have to make a prediction whether you like it or not. I find myself in this position at work that I have to make predictive models, I have to make predictions, and that's just my job, whether I like it or not. There are times that I have data that I don't want to make a prediction on, but you know what? It's not my job to do what I don't want to do. It's my job to make results happen. So something I need to know is how good of predictions do I think I have? And so the framework that we're going to talk about on partitioning our data is our main line of defense on protecting ourselves from making bad predictions. Remember, it's better to have no prediction than a bad prediction. So keep that in your mind as you go forward in predictive modeling. So here's what we're going to do. I'm going to build a model, or actually I'm going to take my data. I'm going to take a subsection of my data, let's say 70% of my observations, and all of the models I build are going to be on this subset of data. We're going to call this the training data set. All right, so the data that I build my model on, my models, is going to be the training data. All right, so now let's say off of this, I've built 10 predictive models. Now, some models are going to be better than others, right? And I want to know which one's the best or which ones are the best. All right, so what I'm going to do, I'm going to take my models. I'm going to take another collection of data, let's say 15% of my original data, and we're going to run predictions on that 15%. Okay, and then I'm going to look to see how well did the models make predictions compared to the data in the validation data set. And hopefully, the comparison will be very favorable, hopefully. And if I don't see anything very good at this point, I'll go back, I'll start working on my data prep. I'll start working on my model building. Let me tell you this, something that is super important, and this is not emphasized enough in the field of predictive analytics. Data prep and data quality, I should just say data quality. Data quality is far more important than your model. Let me emphasize that. Data quality is more important than your model. You go online and you see people talking about neural networks and random forests and decision trees and Mars and Lois and all these mathematically crazy things. They're interesting, they're exciting, they're sexy. You know what? You're not going to get that much better than with other types of model structure if you don't work on your data quality. Data quality is king. Also, when I say data quality, the earlier in the process a step is, the more important it is. So the data collection phase is more important than data prep. Data prep is more important than model building. Because if you do something poorly in the process, any mistake you made, any poor judgments that you have, propagate through the entire process. So the most important step is really your data collection. This is not a data collection class. This is a data prep class. So we're not going to talk about that. If you want to think about data prep, take experimental design. I highly, highly, highly recommend that class. That's far more important than what I'm talking about in this class. Just letting you know. All right, so after I have taken my validation data and I have evaluated how good my models are, I'm going to pick my best one. Okay, I'm going to pick my best one model, or maybe a few. It depends on the project I'm working on, but more than likely, I'm just going to pick one. Now, I want an honest idea of how well that model is going to perform when I make actual predictions. Okay, so what I'm going to do, I'm going to take the last chunk of the data I have to work with, and that's 15%. We're going to call it the test data set. And I'm going to do just what I did with the validation set, but I'm only going to do it on the one best model from the validation. And what this is going to do, this is going to give me what we call honest feedback about how well the model will perform. All right, so this gives me an idea what is going to happen. At this point, I can say, if I have the option to, I want to back out of a project or improve my data or work on my models more. If I see that the accuracy is not going to be good enough, if the model's not going to perform well enough, I need to do something about it, right? I want to keep my job. Then after I'm at this point, after I'm comfortable with my models, after I have faith in my models, I'm going to take the data that is I need to make predictions on. And so, like, for example, let's say I'm going to try and predict who wins the Super Bowl. All right, I'm going to take last year's data. Now, let's say that this was like before COVID was a thing. I'm going to take the data from last season. I'm going to build models, and then I'm going to make predictions on preseason data for the upcoming season. And then I'm going to make a prediction. That's how I would do a situation like this. So the reason why I'm talking about this is if I'm making a prediction about the Super Bowl, I'm making a prediction before the Super Bowl has happened, right? Otherwise, it wouldn't be a prediction. So in preseason, I can go through, take all of the previous data, build a bunch of models, drop the preseason data into there. So I take preseason from last year, I build the models, I take preseason from this year, make my predictions, and I hope I make a good prediction. That way I can laugh at my coworkers when I win fantasy football or something like that. Okay, so just to re-emphasize the partitioning of data, the training data is the data that we build our models on. It's about 70%. A lot of people will go with different numbers. I'm throwing out 70 just for fun. Validation, I use the validation data to decide which model is the best one to use for my predictions. And then my test data gives me an honest estimate on how well the model will perform. Now, with these three parts of the data, I have full and complete knowledge of everything. I know what the target variable is. All right. Down here, the scoring data, this is the data I make predictions on. And something that's very important about this, I don't know what the actual target value is. That's why I'm trying to make a prediction on. Now, in my own work, honestly, usually I don't even use a test set. I just go with training and validation, and I don't give myself the feedback of how well it's going to perform because I'm going to be using it anyway. I would rather put that data into training or validation to get better estimates there. Okay, now when it comes to model performance, my personal experience is that your training statistics will in general be better than your validation statistics, will be better than your test statistics, and will be better than your the actual model performance. Okay, so you'll hear textbooks and videos talk about the test data giving you an honest estimate or something like that. I can tell you things change. The relationship between your predictors and your target variable will change in the time between building the model and getting the new data. Things are going to change. This is going to happen. This is why predicting the stock market is as difficult as it is, because things are always changing. So just realize that your test statistics the model evaluation on your test data will always be optimistic. Just be ready for that. I've been pleasantly surprised a few times, but overwhelmingly it's optimistic. It's not horribly optimistic in my experience, but it's optimistic enough that I just know that it's not good. It's probably not going to be that way. Now, when it comes to the validation statistics, one thing that you can expect to see that is that if I build a lot of models, let's say I build 1,000 models, on my validation data, I'm going to pick the best one. Okay, so if I pick the best one, then I am really incorporating a bias system from the view of a statistician. So what you will see is that your validation statistics, the more models I build, the more optimistic the validation statistics are going to be. So watch out for that. If I go through and I build 1,000 models, and I pick the one that has the best validation statistics, I'm probably, I'm probably too optimistic on that number, just to let you know. If I see the validation statistics are substantially better than tests, that's a sign that I'm kind of getting into that fuzzy area. If the validation statistics are getting close to the training statistics, then I know that I'm in like that I'm getting risky manner. So just be mindful about that. Now your training statistics that is from evaluating your model based off of the training data, or you built the model on the training data. The model is optimizing on that data. It's going to be as good as it possibly can be. So when you look at this, you know that this is horribly optimistic. And just be ready for that. So if you see that the training statistics are pretty close to the validation statistics, then you gotta be like, I might be doing something a little bit wrong. I need some feedback. I need to start like looking at this. Most of the time that will happen when you start building a lot of models. We also use training statistics for the purpose that if I see that my training statistics are worse than validation or test statistics, then I probably have outliers in my training data. And I probably did not filter out my training data properly before starting the project. All right, so let's do an example. I'm going to use the German credit data from the Carrot package. And so here, all of this chunk of code that I'm going through right now, this is just code that I use to prepare the data. You can look through it just for the purpose of this video. Just go, he has data, he's building models, and he's partitioning data. All right, so now I'm going to partition the data with base R. All right, I missed the word base R there. I'm sad. All right, so what I'm going to do, I'm going to use the sample function to create a vector that says train, validate, or test. And I'm doing a 70-15-15 split. And then I'm creating this as a column in my data set. I'm calling it partition because that's how I'm partitioning my data. And then what I do is I split my data using the split function. Didn't really need to do this, but I kind of want to emphasize the next point that I'm about to show. A lot of times I don't bother doing this. I just work with sub data frames. And so just to show you what this looks like is that in my training data, I have approximately 70% of my observations. So this data set has 1,000 observations total, by the way. So here, just under 70% is in the training data frame, and then just under 15% are in the test set, and just over 15% are in the validation set. All right, and that's pretty close. So when I'm, partitioning things like this using random numbers, it's not going to be exactly the way it's not going to be exactly 70-15-15. And that's okay for the vast majority of projects. If it's not okay, then just do something a little bit more cumbersome. All right, now, as I go through this partitioning, model building, and evaluation, this is actually not the way that I would do it in real life. I would use the Carrot package from R to perform all these steps. I'm going through this step by step because I want you to see what is the process that's going on. Carrot enables us to skip over a lot of things easy peasy lemon squeezy. And in real life, I recommend that that's the way you do it. But for the purpose of seeing what's going on, I want to just kind of like go through it step by step with base R. Hopefully we understand what's going on. So now let's go ahead and train our model. So one thing that I like to do to keep my workspace clean is I put all my models in a list. And anytime I have similar structure output, I keep them into a list. And that way it makes my workspace clean, and it makes it easier to find what I'm looking for. And I can use functions like lapply, sapply on the list to iterate over things to make things faster for me. So what I'm going to do, I'm going to make a list, and it's going to contain all the models I built. In this example, I'm going to build 2 models, a logistic regression model using the GLM function, and a random forest using the ranger package. All right, so here I'm going to go ahead and build the formula. So here I'm saying that class, so in this data set, the person either has good or bad on the result of a loan. Either they paid it off or they didn't, good or bad. And here are my predictors. And here what I'm doing is I've got a large formula to work with. Now in R in general, we want to avoid using formulas. They're slower than other techniques. Like the carrot package, you don't have to use a formula. You can if you want. I recommend not using formulas if you can. Some functions will work without them, some will not. You have to be flexible. Unfortunately, R is open source, so the functions can be very inconsistent. But for our purpose, a formula is fine. But basically, you can see that we are predicting the result, the classification of the loan based off of these predictors. All right, so here I'm going to use logistic regression. So I'm using the generalized linear model function. Family is equal to binomial. So this is the logit link function. Now here I'm using the ranger package. And later on, I'm going to want the probabilities instead of the classification. So I set probability equals true. All right, so now at this point, I have a list with 2 models that can make predictions for me. So now what I want to know is, are these going to give me good predictions? Which one is the best? Which of the 2 is the better? And how reliable are they? How far off are they going to be? All right, so how am I going to measure model quality? Well, I feel that mean absolute error is the best way to go. Okay, so in regression, we know about mean squared error. Take the error, square it, add them all up, and then divide by the number of predictions. All right, mean squared error is good, but like when I start talking to decision makers, if I say, here's the average squared deviation from the model, they don't know what that means. Like, it's stupid. But if I do mean absolute error, I can say that, well, on average, the predictions are off by 5. And then I can let the decision maker just, in their mind decide, is 5 okay? Or is it not? But if I say like the mean squared error is equal to 5, they're like, well, you're squaring it? Why are we squaring it? That doesn't make sense. Like, it just doesn't jive with them. So I know that when we're talking about like linear regression, mean squared error has some theoretical properties, and it has some utility in terms of parameter estimation. But to everybody besides statisticians, mean absolute error is the better way to go. Okay, so what I'm going to do, I'm going to create a vector that stores the mean absolute error from each model. Now, vTarget, this is a vector of all the target variables, of the target variable. And I'm going to say it's 0 or 1. It's 0 if it was bad, and it's 1 if it's good, because that was the structure of how the modeling was being conducted. So then I go through and I make a prediction. I take my predictive model, which is stored in list model, and then I say that the new data is the validation data set, and here I have to say the type is response. By doing this, this is going to give me the probabilities. If I don't do that, it's going to give me log odds because of the structure of logistic regression. Now down here, I need to make a prediction with the random forest. So this part looks similar to the previous, but this gives more output than the general linearized model. So I have to say predictions, and it actually gives me a matrix of predictions, bad and good columns. And here I only want the good probability. And so what I'm going to do, I'm going to take the difference between the observation. So here, V target is 0 or 1. If it's bad or good, bad is 0, 1 is good. VGLM, this is each of the validation observations predicted probability or modeled probability of being good. Now here, V Ranger is Ranger's modeled probability of each validation observation being good. I'm going to subtract the difference, take the absolute value, and then I'm going to take the average. Okay. And that's going to be my validation statistics. Now, for the moment, I'm not going to look at it. I'm not going to worry about it. Don't need it yet. Now, I can do the same thing on my training data. There, it's conceptually very easy, easy peasy, lemon squeezy. Now, we do not use this to make an inference, because if I am overfitting, this is going to look really, really good. No matter what happens, the statistics from our training data will be optimistic. If I am overfitting, just like anytime you say over something, it's bad, right? Overfitting is bad. The more I overfit, the more optimistic it will be. And if it's unrealistically optimistic, then that's bad for me in terms of knowing what decisions to make. I want the most accurate information possible, not optimistic information. And so I go through the same process, but you'll notice I've got train instead of validation every single time. And then I'm going to do the same thing that I just did with the validation set and the test set on the test data. Test, test, and test. Okay. So now I've got all that. All right, so what am I going to do? I'm going to look at my validation data. I see that generalized linear model is about 3% better than Ranger. So now remember, this is the mean absolute error. So this is 0 or 1 for the actual bad or good, minus the modeled probability of being good. Okay, so if the model probability is close to 1, then the model is saying that this person is unlikely to default. If the model probability is close to 0, this is saying that the individual is likely to default on the loan. And here we're looking at the difference between the model probability and the actual outcome. Okay, so here I say I should use generalized linear models. Now, one thing I'm going to do now is I'm going to look up here and I'm going to compare these numbers to here. You'll notice that both times training is better than validation. It will almost always be like that. If I see that training numbers are better than validation numbers, I worry that I have an outlier in my training data. I need to go back to my data, either kick it out or impute some values, and then rerun the whole process. And now I've decided that I'm going to go with the generalized linear model. I'm going to use logistic regression for this problem. All right, so now I want an honest estimate of how things are going to perform. All right, so here I get 0.31. Okay, so something that's very nice about logistic regression and regression in general is that they tend to perform, the validation and actual performance in real life tends to be very close compared to other models. As long as I make sure that I don't have too many parameters, too many predictors in there, it usually works out pretty well. And so here, my honest estimate of the difference between modeled probability and outcome, absolute value, average, is going to be about 0.3. All right, well, that might be good enough. That might not be good enough. So I need to look at the situation and judge for myself. Can I launch this model in real life? It might be that there are not better alternatives out there. It might be I need to make predictions and I need to get to another project, and I launch this model uncomfortable with how well it will perform. That's how employment works. So, I need, how we use a model. Do we launch it? Do we not launch it? Sometimes I've made predictions and I wasn't comfortable with it, so I kept it to myself. I didn't let anybody know. I just said, oh, I can't do it. Other times I made predictions and I was okay with it, but not like enough to stake my reputation. So I showed my immediate supervisor, but nobody else. And there are times I made prediction. I said, before, the big wigs in the organization, this is what's going to happen. And I've never been burned in that situation. I have been burned when I shared with my supervisor because of things changing between the relationship of the data and the target variable. But that was something that was beyond my control. That's something you have to be mindful of. So hopefully this has been illuminating. This is all I got. Take care and goodbye.